In this video, we will first examine conductors and insulators, charging by conduction, charging by induction, and a few other matters. First, let us consider metallic conductors. If we look at a metallic wire, we will see that inside we have a lattice of positive ions, that is, a regular repeating arrangement of positive ions, and then some free electrons scattered throughout, which can freely, easily move. These positive ions consist of the nucleus of the metal atom plus its inner electrons. Only the outermost electrons can become free electrons. These free electrons, as mentioned previously, are free to roam throughout the metal. These are the conduction electrons. The ions, however, are fixed in place. They can vibrate, but not really move around. If we now bring a positively charged object near one end of this metal object, what happens is that the electrons, being negative, are attracted to the positive charge and move to this end of the metal. The ions are fixed in place, so they can't move. What do we see? This end of the metal has more electrons than ions on average, and so this end is overall negatively charged. This end has less electrons than ions on average, and so this end of the metal is positively charged. The metal has become polarized due to the movement of the free electrons. Now let us consider insulators. Let us first consider a single atom of the insulating material. In this single atom, the nucleus is at the center, and the electron cloud is distributed symmetrically around it. If we look at only the positive charge, which is in the nucleus, the center of the positive charge is here in the center of the nucleus. And now if we look at only the negative charge, which is due to the electrons, the center of the negative charge is again at the same spot in the center. This, however, is only when the atom is by itself. If we bring the atom near a charged object, the atom distorts. For example, if we bring a negatively charged object near the atom, what happens? The electron cloud distorts away from the negatively charged object because it is repelled. The nucleus is here, where the center of the positive charge is, but now the center of the negative charge, the center of the electron cloud, has separated and moved slightly away. Similarly, if you bring the atom near a positively charged object, the electron cloud distorts towards the positive charge. And once again, there is a separation between the center of the positive charge and the center of the negative charge. This separation is incredibly tiny because it is less than the size of an atom. So it's on the order of tens of picometers. This process of the separation of charge is called the polarization of the atom. Notice that because we are dealing with a single atom of the insulator, the electrons aren't free electrons, they are bound to the atom, but they can distort their distribution. Let's now consider a block of this insulating material. If we place this block between a positively charged plate and a negatively charged plate, each of the atoms inside the block become polarized. The positive center of charge moves to one end, and the negative center of charge moves to the other end. This happens to each of the atoms. But now, let's look at this region. The positive charge centers of these atoms are pretty close to the negative charge centers of these atoms. So in this region, the net charge is effectively zero. The same can be said about these regions. In these regions, the positives and negatives neutralize each other. But if we look here, we see that there is positive charge, but no negative charge to neutralize it. At least none within the insulating block. And so what we see is that this insulating block, after becoming polarized, has an effective positive charge on one end and an effective negative charge on the other end. This is similar to what happened with the metal. The only difference is the amount of charge will be much smaller because it is much harder to get charge separation in an insulator than it is in a metal. In a metal, the free electrons can move easily, leading to a very large amount of charge separation. However, in an insulator, each atom can only distort a small amount. This separation shown here is very exaggerated. The small distortion leads to a small accumulation of charge on either end, and so some polarization. Polarization is responsible for a common phenomena that we see, which is when uncharged objects get attracted by charged objects. For example, if you comb your hair and then bring the comb near some uncharged pieces of paper, the comb, which has become charged by running the comb through your hair, then attracts the uncharged pieces of paper. How does that happen? Let's look at a similar system where we have a charged rod and an uncharged metal ball. If the rod is positively charged, the metal ball becomes polarized, with negative charges accumulating on the surface of the metal close to the positive charge, and positive charges accumulating on the surface of the metal furthest away from the positive charge. Since the negative charges are closer, they feel a stronger force compared to the positive charges, which are further away. And so the attractive force outweighs the repulsive force. Since the net force is attraction, the ball moves towards the plastic rod. Similarly, if the rod was negatively charged, the ball would become polarized the other way, with the positive charges near the negative charges on the rod and the negative charges on the ball on the side furthest away from the negative charges on the rod. Notice thus that a neutral object can be attracted to either charge, whether positive or negative. Because of this, if you see two objects being attracted to each other, you can't be sure that both of them are charged. It could be that one of them is charged and the other is neutral. In fact, occasionally you can see attractive forces between two neutral objects as they spontaneously get polarized and then attract each other. This is responsible for some of the short-range attractive forces between atoms and molecules, like London forces and Van der Waals forces. Again, the important thing to note is that if you want to be sure that two objects are both charged, the surest test is repulsion. If you see them being attracted, you still can't be quite sure that they are both charged. We will now move on to ionic conductors, but first let us discuss the water molecule. The water molecule consists of an oxygen atom which is bonded to two hydrogen atoms. The bonds are covalent bonds, which means that the hydrogen and oxygen share electrons. Each of them contributes one electron. The hydrogen started with one electron and is sharing one electron from the oxygen, and so it has a total of two, which makes it similar to helium. Similarly, each of the hydrogens contributes one electron, and the oxygen atom started with 6 in its outermost shell, so 6 plus 2 gives it an outer shell of 8, which is similar to neon. In this way, these covalent bonds help each of the atoms achieve a filled outer shell. However, the oxygen atom is more electronegative than the hydrogen atoms. As a result, the shared pair of electrons is pulled slightly closer to the oxygen atom. And so we say that the oxygen atom has a slight net negative charge, and each of the hydrogen atoms has a slight net positive charge. When we dissolve an ionic crystal such as salt in water, let's imagine that this is NaCl. The yellow positive ions are positive sodium ions, and the green negative ions are chlorine ions. As they get dissolved in water, each of the ions is surrounded by water molecules. Since the oxygen atoms in the water molecules each have a slight negative charge, they arrange themselves around the positive sodium ion. Similarly, the slightly positively charged hydrogen atoms in the water molecules arrange themselves around the negatively charged chlorine ion. And so, in the solution, that is the salt solution, of NaCl in water, we have sodium ions, which are positively charged, and chlorine ions, which are negatively charged. If we were to put two rods connected to a battery, the positive rod would attract the negatively charged chlorine ions, and the negative rod would attract the positively charged sodium ions. And so, as a current flows in the water, we see that there are actually two movements. The negative ions move one way and the positive ions move the other way. This behavior of ionic conductors is in contrast to the behavior in metallic conductors, where only the electrons were moving and the positive ions that were part of the lattice stayed in place. Let us now discuss charging by conduction. If we have a positively charged metal ball carrying a charge Q and an uncharged metal ball of the same size, and we touch them, then the charge gets shared. What is actually happening here is that electrons from this ball, once they touch, the electrons get transferred over until there is an equal amount of deficiency in electrons on both balls, and thus both balls have the same amount of positive charge. Since charge is conserved, we see that each of the balls has a charge Q/2. However, this is only because both balls have the same size, and presumably are identical in other ways. What if the balls have different sizes? Again, we start with one ball with a charge positive Q, and we have a larger uncharged metallic ball. We connect the two by a copper wire, where copper is a good conductor. What happens? Again, both balls end up with a positive charge, but which one has more? it makes sense that the larger ball will actually have more positive charge. Why? The positive charges repel each other, and so they like to space themselves out. There's more area on the larger ball, and so they can space themselves out further apart. Since this is easier to do on the larger ball compared to the smaller ball, more charge will go to the larger ball. However, finding out exactly how much more charge goes to the larger ball compared to the smaller ball requires us to learn the concept of potential, and so we will wait to answer that question after a few chapters. One interesting point to note is that if you have a metallic object which is three-dimensional and you put some charge on that metallic object, then all the charge will go to the surface. Why do I say a three-dimensional metallic object? If you just had a flat disk, for example, and put some charge on the flat disk, not all the charge would go to the rim of the disk. Some of it would still be in the center of the disk. However, for a solid three-dimensional metallic object, if you put charge on the object and just leave it alone, then all the charge will go to the surface of the object. Now that we have learned a bit about charging by conduction and conductors and insulators, we can look at an instrument which is sometimes used to investigate charged objects, which is the gold leaf electroscope. Here is a picture of the gold leaf electroscope, and in the next slide we will look at a schematic diagram of the electroscope. The electroscope has a metallic cap and a metal stem that passes through. Here it's labeled as a copper conductor, it doesn't have to be copper. And then at the bottom of the stem there is a gold leaf which can move. The apparatus is surrounded by a glass case and the stem is fixed in place by some insulating material. How is the electroscope used? If we touch a charged object to the metallic plate, since metals are good conductors, the charge will spread over the metal. As it comes down over here, in this case the negative charges will repel each other, and so the gold leaf is repelled and sticks out at an angle. Having learned about conductors and insulators, we understand why this part is made of metal. That's because metal is a good conductor and the charges can move easily. And we understand why the case is made of glass. This is because glass is an insulator, and since it's an insulator, we can safely pick it up using the glass case without fear of disturbing the charges that are on the metal part. Here's a question. A gold leaf electroscope is given a negative charge so that the gold leaf spreads away from the stem. Then a negatively charged plastic rod is brought close to the metal cap of the electroscope, but without touching it. What happens to the spread or the angle of the gold leaf? Does the angle stay the same? Does it increase or does it decrease? Pause the video and take a moment to try and think about the answer yourself. In a few moments, we will discuss the answer. We will now discuss the answer. When we bring the negatively charged plastic rod near the metal cap, what happens? The metal part of the electroscope is already negatively charged, and this negative charge is repelled by the negative plastic rod. So the negative charge on the electroscope moves away from the metal cap of the electroscope and down towards the leaf and the stem of the electroscope. Since the amount of negative charge on the leaf and the stem have increased, there is a greater force of repulsion between the leaf and the stem. And so the angle between the leaf and the stem increases. Therefore, the answer is B. We now look at charging by induction. We saw that in charging by conduction, where we simply touch two objects together, when we touch them, the charge on one object is shared with the other object. In this way, both objects end up with the same sign of charge. If one of them was neutral and the other was positive, once we touch them, they both become positive. In charging by induction, we start with an object which is charged, say, negatively, and can create a different object which is charged positively. Let us see how. We start in this case with a neutral metal sphere which is mounted on a glass or plastic stand. A negatively charged rod is brought near the sphere. Since the sphere is metal, it polarizes rather easily, with positive charges on the side near the negative rod and negative charges on the side far away from it. We then connect the sphere to the ground. This black part over here, this symbol, is the symbol for the ground. When we connect an object to the ground acts as a reservoir of charge. In this case, since the negative charge wants to get as far away as possible from the negative rod, it escapes down the wire to the ground. So the electrons leave the sphere through the conducting wire and go to the ground. The positive charges are held in place by their attraction to the negative rod. We now remove the grounding wire. Again, there's no change for the positive charges, they're still being held in place. And now finally, we remove the negatively charged rod. The positive charges were previously held on this side by their attraction to the negative rod, so once the negative rod goes away, the positive charges spread out over the sphere. In this way, we have now charged the sphere with a positive charge. Notice how we started with a neutral sphere and a negatively charged rod, and we ended with a negatively charged rod, which has now been taken away, and a positively charged sphere. The excess electrons on the sphere were removed to the ground. Let's look at another example of charging by induction. Here we have a gold leaf electroscope and a positively charged rod is brought near. What happens? Negatively charged electrons accumulate on the cap of the electroscope, and the gold leaf acquires a positive charge. We now ground the electroscope. What happens? The negatively charged electrons on the cap stay there because they are still being attracted by the positively charged rod. And in fact, more electrons come up the ground through the wire and come in to neutralize these positively charged ions. So, even though it was the cap, which is negatively charged, that was connected to the grounding wire, the negative charge does not go away, because it is being held in place. Instead, it is the other charge, the positive charge, which is neutralized instead. If you like, you can think of it as the positive charge running away down the wire to the ground. Of course, what is physically happening instead is that electrons are going up the grounding wire to neutralize the positive charge. After that, we remove the grounding wire and then remove the positive rod, and the remaining negative charge spreads out evenly across the electroscope. This was an example of charging by induction. That's the end of this video. I'll see you in the next.